This is section 9.1, polar coordinates. Your I can statements for this section. I can graph points with polar coordinates, and I can graph simple polar equations. So far, when we've been graphing equations, we've been graphing them in a rectangular coordinate system. When air traffic controllers record the location of airplanes using a distance and an angle, they use what we call polar coordinates, or they are plotted on a polar plane. In a polar coordinate system, the origin is fixed at a point O that's called the pole. The polar axis is an initial ray from the pole and usually is horizontal and directed towards the right. The location of point P in the polar coordinate system can be identified by polar coordinates that are in the form of r and theta, where r is a directed distance from the pole to the point and theta is the directed angle from the polar axis to the segment OP. When we go to graph a point given its polar coordinates, remember that positive values of theta indicate that we're going counterclockwise, and negative ones indicate that we're going to go clockwise rotation. If r is positive, then P is going to lie on the terminal side of theta, but if r is negative, it's going to lie on the opposite ray of the terminal side of theta. Just as rectangular coordinates are graphed on a rectangular grid, polar coordinates are graphed on a circular or polar grid represented in the polar plane. So this is a polar grid. When we go to graph, the first coordinate tells you the radius of the circle that you're going to go to, and the second value tells you the angle in which you're going to go. So we're going to go to the angle 4 pi over 3, and we're going to go out to the third ring. So we find 4 pi over 3, we start at the center, we go out 1, 2, 3 rings, and we put a dot, and that will be point P. Now if we look at 150 degrees, we are in radian measures on this grid. So the first thing we can do is convert this to radians. Remember, to convert from degrees to radians, we do 150 over 1 times pi over 180. 30 goes into both of these. 30 goes into this 5 times. 30 goes into this 6 times. This is going to simplify to be 5 pi over 6. So if we go to 5 pi over 6, that would be this segment right here. But we're going a negative 3.5 units. So instead of going towards that positive direction, we're going to continue that line but going in the opposite direction away from the 5 pi over 6. And we're going away by 3.5 units. So we go 1, 2, 3.5 rings and then put the dot. So again, you find your angle. Because this value is negative, instead of going towards that angle, you go away from that angle and then plot your point. In a rectangular coordinate system, each point has a unique set of coordinates. This is not true for polar coordinate system. You learned that a given angle has infinitely many coterminal angles. As a result, if a point has polar coordinates r and theta, then it also has polar coordinates of r and theta plus or minus 360, or r and theta plus or minus 2 pi, depending on if you are in radians or degrees. Additionally, because r is a directed distance, r theta and negative r theta plus or minus 180, or negative r and theta plus or minus pi represents the same point. So just like we looked in that last example, 5 pi over 6 and 11 pi over 6 are pi away from each other. They're half a circle away from each other. So if we want to do the negative r, we just do 180 or pi away from that original point. In general, if n is an integer, the point with polar coordinates r theta can also be represented by polar coordinates of the form r and theta plus 360 times n, or negative r theta plus 2n plus 1 times 180. You can do the same thing with your pi's instead. So we need to find 4 different pairs of polar coordinates. They do have to be between negative 360 and positive 360 that are representing this point. So the obvious one is we go out 1, 2, 3, 4 places. So the obvious one is 4 and 135 degrees. Now you can find another one by adding or subtracting 360. Now if we add 360, this is going to be more than 360 degrees, so we don't want to use that because we need values between negative 360 and positive 360. But we can take 135 and subtract 360. And this would give us 4 and negative 225. So now we have 2 solutions. We need to come up with 2 more. The other thing we can do is we can make it a negative r value. When you make it a negative r value, you can add or subtract 180. So if we do 135 plus 180, this is going to give us negative 4 and 315. And if we do 135 minus 180, this is going to give us negative 4 and negative 45. So our 4 solutions are here. An equation expressed in terms of polar coordinates is called a polar equation. For example, if we have the formula r is equal to 2 sine of theta, this is a polar equation. A polar graph is a set of all points with coordinates of r and theta that satisfy a given polar equation. Now we're not going to actually work on graphing the more complex equations in this section of r equals 2 sine of theta, but we're going to start with the 2 basic ones. 2 basic equations can be r equals just a number or theta is equal to just a number. If it's r equals, this is telling you the radius, so that means you are graphing a circle. So on part A, we're graphing r is equal to 2. This means we go out to the second ring, and we would just draw a circle on the second ring, and that would represent r is equal to 2. On part B, we are graphing theta is equal to pi over 6. This just means we're going to have a line. It's going to go in both directions. It's going to go towards pi over 6, and it's going to go away from pi over 6. So this would be an equation of theta is equal to pi over 6. It is possible to find the distance between 2 points in polar. Your first point, P1, is R1 sub 1 and theta sub 1. Your second point, P sub 2, is R sub 2 and theta sub 2. These are 2 points in the polar plane. To find the distance between those points, we do the square root of R sub 1 squared plus R sub 2 squared minus 2 times R sub 1 times R sub 2 times the cosine of theta sub 2 minus theta sub 1. An air traffic controller is trafficking 2 airplanes that are flying at the same altitude. The coordinates of the planes are A is at 5 and 310 degrees, and B is at 6 and 345 degrees. What are the directed distances in the measured, where the directed distance is measured in miles? So the first thing we need to do is sketch a graph of their solutions. Because we do not have 6 rings, let's let each ring represent 2. So this would be 2, 4, 6, 8, and 10. Our first point is at 5 and 310 degrees. 310 degrees is not going to be exactly on any of the lines. 310 degrees falls between 5 pi over 3 and 7 pi over 4, because 5 pi over 3 is 300 degrees, and 7 pi over 4 is 315 degrees. So it's going to be closer to the 7 pi over 4. And we are going to go out to 5. So halfway between rings 4 and 6. This would be point A. Point B is at 6 and 345 degrees, so we would be here. Now we're trying to find the distance between those 2 points, because for part B, it says if regulations prohibit airplanes from passing within 3 miles of each other, are these airplanes in violation? So we need to see if these planes are closer than 3 miles apart, then they're in violation. If they're farther than 3 miles apart, they are not in violation. So our formula to find distance now, depending on what information they give you in the problem will determine if your calculator needs to be in degrees or in radians. If your angle measures in degrees, your calculator needs to be in degrees. If your angle is in radians, then your calculator should be in radians. So we're going to have 5 squared plus 6 squared minus 2 times 5 times 6 times the cosine of 345 minus 310. You can put all of that into your calculator at the same time, and we're going to get that D is approximately 3.44 miles. So this means that the airplanes are not in violation of the regulation.